I used to live near the desert of the Australian outback, and one of the things that amazed me most about that experience was that at the end of the day, after a 40 degrees Celsius heat wave, the nights could get freezing cold, often below zero. Near the coast, though, this wasn't the case at all. In fact, I may have gone swimming at Bondi Beach in downtown Sydney after dark a few times. So why is it that temperatures seem to be more moderate in coastal places, while inland zones tend to suffer from more extreme temperature fluctuations? To understand this, we'll need to understand energy and heat. So to start today, I want to let you know about the first law of thermodynamics. It's a relatively simple one. It states that energy cannot be created or destroyed. I like to think of it like currency, almost like cash, right? We're not allowed to print out our own. We're also not allowed to destroy it. It can only be transferred from one person to another, or one entity to another. And energy is essentially the same. We can convert energy from different forms, like electronic energy to kinetic energy or to heat and back and forth, and we'll talk about all of those today, but we can't create or destroy energy. And that's a fundamental concept, and that's going to help us a lot when we're trying to understand the energy of chemical processes or the energy of chemical entities themselves. So, first law of thermodynamics is that we cannot create or destroy energy. We can only transfer it back and forth between entities or between forms. So that's the first important thing to think about. The next thing is, though, the thought of really what is energy in a chemical context. What does that mean? What does it mean to say that something has energy? Well, in chemistry and essentially in all sciences, we generally think about energy as coming in two different forms. We think of kinetic energy, right? Kinetic energy is the energy of motion, right? And I think that makes intuitive sense. If a particle is moving, it must have energy, right? Energy is, strictly speaking, the ability to do work. That would be more of a strict definition of energy. Can work be done? Can something useful be done? And if it can, then energy is what it costs to do that potentially. But that's not always super useful. I like to think in chemistry in terms of kinetic energy as the energy of particles moving. If particles are moving, they can collide with other particles and they can, cause motion to happen, which might potentially be used to do work. It doesn't have to be, but moving particles seems to me to be an intuitive notion of some energy. But that's really only the kinetic part of energy. We've talked about this in terms of the kinetic molecular theory of gases. We said that particles were moving, and that meant that they had energy. And if we increase the temperature, we increase the average amount of motion that was happening between those particles. And all of this is interrelated, but this is kinetic energy, right? So the energy of motion. The other type of energy we think about in science, and in particular in chemistry, is potential energy. And this one's a little bit more cryptic, a little bit less intuitive, but I like to think of potential energy as the energy of position, right? So where I'm at, I don't have to be moving, but simply the position that I'm in sometimes dictates an amount of energy that I either have or that I could have. So let's think about that. So kinetic energy, as I said, is the energy of motion, and potential energy is the energy of position. Imagine, if you will, you had a couple of different particles. I don't know, maybe it's a sodium ion and a chloride ion, for example. And as they're floating around in solution, you might imagine an attractive force that would exist between those two. So if you were to hold them at a fixed distance apart, they would have a Coulombic force of attraction, right? And if you were to let them go, they would then snap together, so to speak, and then they would be, potentially be flown off into space as a result of them snapping together really quickly. This is sort of a cartoony type example, but let's think about what's going on there. The force of attraction, that Coulombic force of attraction between those two particles, is a potential energy. It has to do with position. It has to do with where they are in space. If you were to bring those two particles to some, very large distance from one another, then that force of attraction is not so great. So that is really positionally dependent. It is an energy of position. And if you were to, bring them close enough together so that they could interact, and they all of a sudden flung together and snapped together and then started flinging off through space, that would be an example of potential energy being ultimately converted to kinetic energy. But potential energy, suffice to say, is the energy of position. Another way to think about this is that it actually costs you energy to pull those particles apart. Suppose they were together and you had to pull them apart. You have to put energy in to do that, right? You have to put energy into that system. And that essentially increases the potential energy of that system. So nonetheless, to sum all this up, the energy of a chemical system is determined by the motion of all the molecules or particles we have, and also the potential energy, the positions of all of those particles, because they interact through space. So if we could sum all of that up, all of the motions of all of the particles and all of the positions of all the particles and how they all interact with one another, all of that summed up together would be called the internal energy of the system. So the internal energy, often given the symbol uppercase U. This would be our internal energy. All of the kinetic energy of all of my particles and all of the positions of all those particles, that would be potentially useful, but we would call it the internal energy of the system. Now, it's a bit nonsensical because there's no real way to go in and take a measuring tape and measure where all of my particles are and then how fast they're moving at the same time. In fact, Heisenberg's uncertainty principle would have something to say about that. But what we're going to have to do instead is, instead of literally calculating what the internal energy is of any particular system, what we become more concerned about is what is the change in internal energy. So maybe I don't care about what the absolute internal energy is for any particular chemical system, but it is important for me to understand how that internal energy changes as I go from one state to some other state. And so the delta U, or the change in internal energy, is an important quantity in science, but also in chemistry. So let's ask ourselves, how can that internal energy change happen? How can my internal energy change? Well, I've alluded to this before, but it can change if I heat up my system. And so suppose we were to keep track of heat energy. If I were to add energy via heat or subtract energy, so somehow cool my system down, let's call that Q. So if I were to add some heat energy to the system, again, or subtract heat energy from my system, in which case Q would be a negative number, then I would obviously change the internal energy of the system. But there's also other things that I can do. I can do work, or the system can do work, right? So there's all kinds of ways for chemistry to do work. And you think of the steam engine, for example, where pressure is built up inside some pistons, and that pressure is caused by high pressure steam, and then the piston moves, and then you can move a wheel or anything else with that. That's chemistry doing work. That's particles using their internal energy to apply force, which ultimately does work after that. And that would, of course, change the internal energy of the system. Likewise, I could, say, compress a gas in a piston. I could do work on that system, and the internal energy would, of course, change as a result of doing this. So this is a general way for us to write out how the internal energy of a chemical system could change. I could heat it up or cool it down. In other words, change the heat energy, or I could do work on that system or have that system do work, externally. And so both Q and W could either be a positive number or a negative number, but it's a way for us to sum up all of the changes that could result in a change in internal energy. So what are we going to do in this class? Well, as I mentioned, that really this is all about energy and heat. Most chemical processes that we're interested in studying happen on a benchtop, happen under constant pressure conditions. Just out on a chemical benchtop, the pressure isn't changing significantly. And so if we say that we're not going to do work on our system, because most often doing work on our system or having our system do work does involve pressure changes. If we're not going to do work on our system and we're instead only going to talk about heat energy changes, and we're going to talk about heat energy changes only at constant pressure, then we can define a new thermodynamic quantity, and we can call it the enthalpy. Enthalpy, the enthalpy, given the symbol uppercase H, and that change in enthalpy we will define as the heat energy, either put into the system or taken out of the system, but more specifically, the heat energy at constant pressure. So I'm going to put a little subscript P on here to indicate that this is constant pressure. So this is a relatively simplistic picture relative to total internal energy. I'm only going to worry about total internal energy at constant pressure, and I'm only going to worry about heat energy changes. And so instead of total internal energy, I've got what could be thought of as a subset of that, and really just this quantity called enthalpy. So enthalpy has to do with the amount of internal energy that changes in a chemical system due to heat energy specifically being added or removed at constant pressure. So this is enthalpy, and this is what we'll be concerned about when thinking about energy and more specifically heat in chemical processes. So how are we going to measure these energy changes? Well, we'll talk about measurement techniques in a moment, although they're fairly trivial, but the units that we use for energy are the joule. So the joule is a common energy unit given the symbol uppercase J, and this joule is what's called an SI unit or a system international. These are the standard units we use in science. It doesn't mean it's the only unit of energy you've seen or that we'll use occasionally, but it is certainly the most common. And it's, if you want to get a mental picture of a joule is about the energy required to lift an apple 1 meter in height, right? So that's just to give you a sense of what a joule actually is. There is another unit of energy in common use, and sometimes we'll make reference to it, and that is the calorie, given the symbol or the unit symbol CAL. So these calories is a unit symbol, and it's the amount of energy it costs to raise the temperature of 1 gram of water by 1 degree Celsius. So it has a very specific meaning. This is also a unit system that you'd be familiar with from food labeling. Although in food labeling, it's often modified a little bit to be an uppercase C, so uppercase C calorie, which is by definition actually a kilocalorie as I've defined it here. So a calorie on the side of a cereal box, for example, is actually 1,000 of these calories. Right? So those calories is the amount of energy to raise 1 gram of water by 1 degree Celsius. Okay, so these are the unit systems we'll commonly use, and most commonly, of course, we'll be using the joules, which you've already seen in other aspects of this course, but we're going to dive into the units of joules in terms of heat and energy now. All right, so to put all this together to talk about substances, and let's just talk about pure substances for the moment, to take a pure molecular substance and give it enthalpy, to increase its enthalpy, or to decrease its enthalpy, we're talking about temperature changes. And all pure substances, in order to help us with this, have a property known as the heat capacity. So what is a heat capacity? Well, a heat capacity is, as the name suggests, a capacity for heat. How much heat can be stored in that particular material, right? So if I give a certain number of joules to a piece of material, how much does its temperature increase by? Some substances can actually have a very large capacity for heat. Some substances not so much. And this is directly measurable by giving these substances energy and measuring the change in their temperature. And so all pure substances have this thing called a heat capacity, and it's given the symbol C. But you'll often see several differences in how these C's are represented. So for example, sometimes you'll see a heat capacity with a subscript S. So this is what's known as the specific heat capacity for a particular substance. And really, all that means is units. So the units of these heat capacities can sometimes be somewhat different. But let's talk about one, for example. So for ice, for solid water, so this is a molecular substance, obviously, the specific heat capacity happens to be 2.06 joules per gram per Kelvin. Okay, so let's think about that, because this unit is a very useful thing to be able to understand what a heat capacity actually is. Let's take a look at this. Joules per gram per Kelvin. So what this is the number of joules of energy I need to take 1 gram of ice and raise it by 1 Kelvin, raise the temperature of it by 1 Kelvin. This is the amount of energy it costs to do that. And so the phrase heat capacity, I think, makes a lot of sense in this context. It is the capacity for heat energy that this substance has. I need 2 joules of energy to raise a gram by a degree, or raise the temperature of a gram of the substance by a degree. And so if I have much of this substance, if I have an iceberg, it's obviously going to take a lot of energy because my mass is very high. I have to multiply this by all the grams that is contained in the size of the substance I want to increase. Likewise, if I want to increase its temperature by a lot, it's going to take a lot of energy to do that. It's going to take twice as much energy to increase the temperature by 2 degrees than to increase the temperature by 1 degree. So you can even intuitively see how we might measure these heat capacities, to provide energy to a system and see how quickly its temperature rises. And so this is heat capacity. Some of the other ways you might see heat capacity in your studies is maybe with a little subscript m. So with a subscript m, this would be referred to as the molar heat capacity, which I think gives you a hint as to what we're actually talking about here. For the same substance, that is solid water or ice, it is 37.1 joules, and there's the difference here, per mole per Kelvin. Okay, so this is a molar quantity. It's actually the same number. It's the same substance. This is ice. How much energy does it take to heat up ice? Well, it's 2.06 joules if you have a gram, but it's 37 joules if you have a mole. And of course, that's because water has a molar mass of 18 grams per mole. So this is just 18 times as big as that number. That's all. But you will often see these heat capacities. And what's most important, I think, is that you focus on the units that are used, both because the units actually, I think, tell me what this quantity really is. It tells me what it means, but it also tells me how to work with it. If I want to know how much energy is required to raise the temperature of this particular block of ice, if I'm using this heat capacity, I need to know how many moles I have. But if I'm using this heat capacity, I need to know how many grams I have. So it's important to watch those units. But again, it also tells me what a heat capacity actually is and what it means. So we've got a specific heat capacity, a molar heat capacity, and sometimes you'll see heat capacities, and we'll talk about those next lecture, that don't have a mass or a quantity in their unit system. And that's because they're standard based on a standard known amount of that substance. So we'll get to that, but that's fundamentally what a heat capacity is. And this is really an important concept when talking about heat and energy transfer, I think for obvious reasons. This is precisely the amount of heat energy required to cause changes in temperature. So a heat capacity, it is a fundamental physical quantity. It's known for all known pure substances, and we can use this to our advantage in a whole host of ways. But first, let's use it in some math. This is a phase change diagram. It's not a phase diagram in the sense that we've looked at before. This is a diagram that has temperature on the vertical axis in units of degrees Celsius, and it has heat energy on the horizontal axis in units of kilojoules. So recalling that kilojoules is 1,000 joules, right? That's what the prefix K indicates here. So 1,000 joules. And so we can look at this axis and see how much energy has been added to this particular substance. What we're looking at here specifically is this heating curve. So we call this a heating curve for specifically 500 grams of water, H2O. So this is a pure substance, and it's 500 grams of that pure substance. And we are plotting the amount of energy it costs to increase my temperature. So really, I just keep adding heat energy, and I keep measuring the temperature of my system, of my substance, my 500 grams of water. Keep measuring the temperature, keep adding heat, and you'll see the temperature change and then sometimes not change, and then change again. And this is a typical heating curve, and we can learn an awful lot from this. So what I want to do is I want to work with this, and I want to use the heat capacity of water. And let's not forget that the heat capacity of a pure substance depends on phase. The heat capacity of solid water is different than the heat capacity of liquid water. It is essentially a different molecular substance. That shouldn't surprise us so much, because we understand that the molecular arrangement of our water molecules in all the different phases is entirely different, right? So the arrangement of molecules in solid water is very different than the arrangement of those molecules in the liquid phase. Likewise, it's different in the gas phase as well. So the capacity for heat, and I'm using that phrase very intentionally, the capacity for heat of all of those different arrangements is different. And that's an important thing to keep in mind, because if we are looking for the heat capacity, say to solve a particular problem, we want to make sure we're using the heat capacity of the appropriate phase. All right. So let's do a question here. Let's actually calculate, if we can, the energy associated with these various lines in this curve. Okay. The first thing we can notice is that it's actually multimodal. So there are several sections of this curve. Notice that if I'm down at -50, I've obviously got a block of solid water. We know that water freezes at 0 degrees Celsius. So this is ice. And I provide a certain amount of energy, which I can highlight here in my diagram by drawing essentially a straight line down here. And so this amount of energy, that takes me from my axis here all the way over here to where this line meets. That's the amount of energy right here required to raise the temperature of my ice up to 0 degrees. Okay, now it's a relatively small amount. We can zoom in here just to sort of see what's going on. If I've got my 500 gram block of ice down at -50, and I want to increase its temperature to 0, which is of course a requirement if I want to melt it, it's going to require this much energy, right? So it's not on the scale per se, but we can predict what it is. We can calculate it. And that's what I want to do right now. So let's do that. We've already been given the specific heat capacity for solid water, right, for ice. And the specific heat capacity, as we discussed a few minutes ago, is 2.06 joules per gram per Kelvin. Now, on the previous image, we have this 500 gram block of ice, and it's at -50 degrees, right? We can remind ourselves of that by zooming back down onto the picture here, and we can see we're at -50. And what we'd like to do is we'd like to heat that ice up to 0 degrees. So if we heat the ice up to 0 degrees, how are we going to do that? Well, let's think about all the things that have to happen. First of all, we know the mass of this particular ice block, and it's 500 grams. We also know that we want to change its temperature by 50 degrees. Isn't that right? We want to change the temperature by 50 degrees. And a change in temperature, if in degrees Celsius, is the same as a change in temperature in Kelvin. So of course, I could take the -50, convert that to Kelvin. I could take the 0, convert that to Kelvin to calculate a difference. But you will arrive at precisely the same change in energy. So this is sort of a little trick that we're doing here. Whenever we have a change in temperature, a change in terms of degrees Celsius is equivalent to that change in terms of Kelvin. And that's because 1 Kelvin, that amount of temperature, is the same as 1 degree Celsius. That scale is identical. And so look at what we know. We know our mass, we know how much we want the temperature to change by, and we know the specific heat capacity. Now, I can give you an equation to solve this problem, but the good news for us here is that just by knowing the heat capacity, the equation is self-evident. We know that it takes 2 joules for every gram, but we know that we have 500 grams. And we know that it takes 2 joules for every Kelvin, but we know that we want to go up by 50 Kelvin. So in my opinion, this is fairly clear that what we want to do here is take our heat capacity, 2.06 joules per gram per Kelvin, multiply it by the mass, which in this case is 500 grams, and multiply it by the amount of temperature change that we want to have happen, which in this case is 50 Kelvin. So we can see that the heat energy is really just given by this series of numbers. And of course, the heat energy, what we're interested in calculating here, is Q at constant pressure. So there we go, and we have our equation. Now this equation you can see is the specific heat times the mass times the change in temperature. Now it's often written such that the mass goes first, but the equation that we've actually just figured out, we didn't actually have to memorize this. The equation is such that the heat energy is equal to mass times heat capacity times the change in temperature. This is generally how we write it, but notice that of course we did the exact same thing here. So putting together all of these numbers, what we end up getting is 51,500 joules. All right, so more conveniently, we could express this in terms of kilojoules by realizing that there are 1,000 joules in every kilojoule. So what I could do is call this 51.5 kilojoules. And if I want to keep two significant figures, I could round this, of course, to 52 kilojoules. And there we go. Now, if we take a look back at the image we were just working with before, we can see that this is about right? And this is 200 kilojoules here. Half of that would be 100, and half of that would be about 50 or 52. And so we've really just calculated this horizontal distance here. We've calculated that it would take about 50 kilojoules to increase the temperature of this particular sample by 50 degrees. And so this is a useful thing. We're going to make use of this in several different contexts, but this is how heat energy is calculated for a particular substance as it changes its temperature. Now, an interesting phenomenon is about to occur. Look at what's happening here. When we arrive at 0 degrees, let's not forget what we actually have here. We have a 500-gram block of ice, solid water, at 0 degrees. It isn't melted. It is a solid block of ice. So it is then possible to melt that, of course. It doesn't melt until it gets to 0 degrees. But at this point in time, it is still a solid block of ice. And what we now need to do is give heat energy to this system for the sole purpose of melting it. Right? So if we keep providing heat energy, the interesting thing happens is that that solid block of ice converts into a 500-gram sample of liquid water, but still at 0 degrees. The temperature doesn't change. All of the heat energy being supplied to the system is going into the melting process. And that's a really important realization. You know, if you've got a sample of liquid water with ice in it, so long as you appropriately equilibrate that, right? So take a glass of ice water, for example. If I see a glass of ice water and I know that it's properly stirred, I know for sure that as long as that's pure, the temperature is 0 degrees. It has to be, because that sample will not be in equilibrium unless it's at 0 degrees. 0 degrees is the only temperature at which solid and liquid water can coexist. So, like I said, if you've got a glass of water and as long as it's pure and there's ice in it, if you stir that up and measure the temperature, you're guaranteed for it to be 0 degrees. So, what is the lesson here? The lesson is that heat energy supplied to that system, right? As the ice melts in my glass, all of the heat energy being supplied by, I suppose, the room or by your hand or by whatever is going into that melting process. The heat energy is going into melting the ice cubes. The ice cubes are like a sacrificial lamb, if you will, for the heat energy coming into that system. The entire system will remain at 0 degrees, definitely, until all of the ice has melted, all of the solid has transferred into liquid. And at that point, we're at this part of the diagram, and the only option left is for the next amount of heat energy to be going into actually heating up that liquid water. So this is an important realization. This heating curve that we're looking at is segmented based on the process. You are either heating up the substance or you are phase changing the substance. And so there are two different ways of calculating the energy change as we go through this diagram. It's either the heating part, which is what we just completed here when we calculated the amount of energy it would cost to heat up my 500-gram block of ice, or it's the phase change process. So how much energy does it cost to change the phase of this substance, from solid to liquid? So that's really the next goal. That's what we have to do. We have to think about how much energy does it cost to change this phase right now. So heat capacity is not going to be useful for us in this instance because we've got two different substances, right? We've got a solid phase and we've got a liquid phase. And we've already talked about the fact that each of those two phases has a different heat capacity. We haven't listed them, but suffice to say that they're different. So, what we've been doing up to this point isn't going to be useful. But there are other constants typically stored and measured for all pure substances. And the enthalpy changes associated with phase changes are those constants. So for example, there are standard enthalpy changes of phase changes. So for example, enthalpy of fusion. Notice my subscript FUS. The enthalpy of fusion for water specifically is a known quantity. It's a tabulated quantity. It happens to be 6.00 kilojoules per mole. In other words, this is a property of water, and it's a property of the phase change of fusion, which is melting of water. And what this tells me, what this constant number tells me, is that it costs 6 kilojoules of energy to melt a mole of water, or a mole of ice specifically, but a mole of solid water. And this is another one of those unique intrinsic physical properties of this substance. And the really nice news here is that it's already answered for us. The standard value here is actually the answer. If I want to know how much energy does it take to melt solid water, I am given the amount of energy it takes to melt solid water. So it is an intrinsic solution to its own problem. And if you think about it, when we solved for the energy change associated with heating up the 500 gram block of ice, this was sort of the same thing. The heat capacity was the constant, the physical constant that described the substance that we needed before we could move forward with the problem, but it is its own answer. It already tells you how much energy. It's 2 joules. It's just 2 joules for every gram for every degree Kelvin. So we just had to multiply by the grams and how much degrees Kelvin we wanted to increase the temperature by. So it is its own answer. And likewise, the energy change associated with a phase change, assuming we're provided with that standard information, it is its own answer. And so in this particular case, the only question that arises is how many moles do we actually have? So let's not forget that we had 500 grams of this particular substance, and it was water. So we know that for water, 1 mole of H2O corresponds to 18.02 grams, right? We can do that calculation just by the molar mass. And so 500 grams divided by 18.02 gives me a total of 27.7. So that's how many moles of water I have if I have a 500 gram block. So I can work with this. I know that my enthalpy for this particular case is going to be equal to the number of moles times the enthalpy of fusion, right? That standard quantity. So I've got 27.7 moles, and the standard amount is 6, let me make that a little bit cleaner, 6 kilojoules for every mole that I have. So this is really all I need to do. And the total amount of heat energy change in this particular context is 167 kilojoules. Now notice I'm using delta H here, but let's not forget that the heat energy associated with a constant pressure system is, of course, delta H. These are one and the same thing. In the previous slide, when we worked out the energy change associated with heating up that 500 gram block of ice, this is also equivalently delta H for that particular process. So these are one and the same thing. So if I take a look at what I've got here, my final answer becomes 167 kilojoules. And if I refer back to my figure here, I can actually try to reason whether this looks right or not. There's the point on the diagram that I'm trying to get to now. And what I've just determined, let me zoom in again, is that this change now to go from here to here was about 167 kilojoules. And so that makes, I think, pretty intuitive sense. Here is 200. And remember, we already calculated about 52, so 52 plus about 160 should take you just past 200, and that's exactly right. So this corresponds. This is, we're getting the right numbers, and this is the physical meaning of what this heating curve actually is. It costs roughly 50 kilojoules of energy to heat up that ice, and then it costs about 160 kilojoules to melt it entirely into the liquid phase. So we're now at this point of the diagram, and I have 500 grams of now a pure liquid sample. Now, if I want to continue on, continuing on is fairly straightforward. The only thing I need are the heat capacities and enthalpy changes of phase change for all of the different segments of this line. And so here I've just indicated all of those constants that are characteristic for this pure substance, which is 500 grams of water, at all of the different phases and for all of the different phase transitions. So here's that specific heat capacity we used before, which describes solid water. Here's the specific heat capacity that describes liquid water. And here's the specific heat capacity that describes gas phase water or steam. Notice that obviously they're all different, but these values correspond to the slopes of these lines. In other words, if this slope is far more flat, as the liquid line is compared to either the solid or the gas phase, that means it takes more energy to heat this system up. There is a higher heat capacity. And as it turns out, liquid water has one of the highest heat capacities of any substance, far higher than the vast majority of metals. And so this high heat capacity has a really important role to play in all kinds of contexts. Likewise, you can look at the enthalpy changes for phase changes. Notice that melting ice costs, as we'd calculated, about 160 kilojoules, but boiling water, look at that number. So much more energy required. Look at the length of this line. And that's all due to that hydrogen bonding, that connection between neighboring water molecules. It's really, really difficult to give enough kinetic energy to that system to break those and cause that water to be boiled. So these numbers are very characteristic of intramolecular forces. But in particular, this specific heat capacity is a big one relative to most pure substances. And that helps us explain the part of the temperate climates of coastal regions. The oceans have an incredibly high heat capacity. And what they do is they help to stabilize climate because they hold so much of the sun's energy. When night falls, they can actually start radiating some of that outward. And when winter arrives, they can do the same from the energy stored over the summer. In other words, the ocean is essentially a giant temperature regulator because it stores so much heat and it stores heat so effectively. And this is fundamentally due to the very high heat capacity of liquid water. So if we didn't have that liquid water, we would be susceptible to wildly changing atmospheric conditions and wildly changing temperatures, as is experienced on other planets without water. So, I mean, for that and many other reasons, water is an amazing substance that, again, as I've said before, is responsible for life as we know it.